Okay, so how is everyone today? Good? This is 2414, right? Okay, good. Just making sure I'm in the right spot. So my name is Dr. Brady McCary, and I'll be your instructor. There was a last-minute change in the instruction schedule, and I got added at the last second. So if you're surprised, I believe that the previous instructor was scheduled to be Dr. Lewis, but at any rate, it's me. Good. So the best way to contact me is by email. My email address is brady.mccary@utdallas.edu. My office is FA 2.402. Now, because this is a fall semester, that means that it's possible that many of you are brand new to the campus anyway. You should understand that on campus there's 3 buildings with Founders in their name, and we're in one of them, and it's called Founders. Just north of here is a building called Founders North, and just west of here is a building called Founders Annex. I'm in Founders Annex. And then the funny, or not really funny, but at any rate confusing issue about it, is that all of these buildings with Founders in their name have a 2.402, I think, and like all of them have math people in it, you know? So it's real easy to like go to some building with Founders and then go to 2.402 and there's a math person there, but unless you happen to be in Founders Annex, that's not where I am. Okay, good. My office hours. Are Monday and Friday, but not Wednesday. Monday, Friday, 11 to 12, and also Tuesday, Thursday, 10 to 11. I'd be happy to see you there. So the way the course will go, the lectures I mean, is that you know, I'll write on these sheets of paper here, and they'll be on the thing there, and then at the end of the day, I scan these and post them for you to look at, you know, if you want. So the purpose of that is just to, you know, in case you think you missed something, or in case you just want to review something, but don't take that as license not to take notes. Because the truth of the matter is that the more engaged you are in the lecture, the more likely it is that you're going to retain something. So I really encourage you not to think of this like a TV show, okay, and just like watch. Okay, you should write something and engage your you know, the physical part of your mind and body. So in hopes that you'll retain some of it. Good. Besides scanning these pages, I also record the lecture with video. It's recording now, and I'll post that on YouTube, and you're free to look at that too. Any questions about that? The syllabus. The syllabus is on e-learning, as well as lots of other stuff. Learning. Concerning assignments that you have to take in the class, we use an online homework service called WebAssign. They're posted, I think there's basically one online homework per week. A message will be sent for, you know, saying that it's posted. We have problem sections that you all had to sign up for. Attendance is mandatory, and you take quizzes there. In about, I think, if I read the syllabus correctly, in about like the 4th week, we're going to post a homework that you have to get a blue book, and you have to write out in long form all of your answers, and you'll turn in that blue book in problem section to the TA, and that'll be graded. And then we have exams. So that's online homework, stuff that you do through WebAssign. There's weekly quizzes in the problem section. There are some written homeworks that are not going to begin until like around the 4th week. A message will be sent when that's finally posted. And we have exams. Any questions about that? Yes?
Yes, until the 4th week, how many books will you need?
For the entire semester, I believe you'll need on the order of like 4 or 5 blue books. Other questions? Yes?
It sounds silly, but is the information about blue books on the syllabus?
Do you mean like where to get one? Yeah, you can go to the bookstore or like Walmart or anywhere. But probably the most convenient place is the bookstore, except that it's going to cost like twice as much as Walmart. But you know, gas and wear and tear on your vehicle is also a concern too. But
I mean, there is a place on campus, I don't remember where it is, but it's sometimes give out blue books, right? Because I know it's in one of the student services.
yeah, there's something like that too, but I don't really know it. Unfortunately, I got assigned this at the last second. Good. Other questions, comments, concerns before we get to math? Okay, so by the time because you're in here, you passed a differential calculus course, and differential calculus knowledge is presumed so that you can calculate the derivative of more or less all the polynomials and trig functions and exponentials and logarithms and things like that. And you've also had a brief exposure to computing antiderivatives and integrals in the fundamental theorem of calculus. Okay, great. We'll review a little bit of that stuff as it comes up. But for reasons of being in harmony with the physics department, we're going to just briefly study a little bit of topics about vectors, and then we're going to jump back into antiderivatives and integrals. So here we are. Here we are in section 12.1. And it's called three-dimensional coordinate systems. All right. Now, before we get to 3, let's just start with 1. So that's a fancy-looking R, and that's the way that you denote the real numbers. But that block, you know, the left leg of the R, it's made like a box. That's the stylistic convention for writing bold on a piece of paper or a whiteboard. You know, because I don't have a bold pencil. Okay, so that means a bold R. These are the reals. The way that we visually denote the reals is with a horizontal line. Like so. Now, you're coming to the place. I know that historically it might have been the case that your instructors wrote arrows going both ways to sort of signify that the line goes all the way to the right and to the left. But you know, it's time to put aside childish things. Okay, so we have to make the arrow just point one way. Now, if you want to be real clear, okay, that the line continues, you can make a little backwards thingy, but like this. That means that it continues going that way. That's its meaning. Now, you might question, you know, well, why is that? Okay. Well, in the end, the reason is because if I take 2 points on the line, say like that red point there, and that green point there, red and green points, then which one has the larger value? The green one. Why is it that the green one has a larger value? It's further to the right. Well, how do you know that right is bigger? Well, how do you know that? It's not. Because the arrow points that way. Okay? So now, what I mean to tell you is that, if I drew a line like this, if I did this one, and then I made a red line, a red point, and a green point, and asked, which one has a bigger value, the red one or the green one? Which one? The red one. Why does the red one have a bigger value? Why is left important? Because that's the direction the arrow is pointing. You understand? Okay, so the arrow signifies the direction of increase. Now, it's been the case that all the time, in your experience, it's always been like that. But it's going to cease being that way. Okay? You have to look at the arrow to understand the direction of increase, the arrowhead, which way it's pointing. All right. Any question about this so far? All right. Now, the real line is a one-dimensional. It's a one-dimensional thing. It's one-dimensional because you've kind of got to use your imagination a little bit here. What if you were this red point, and you were allowed to move around on the line? Okay, but that's the only place where the whole universe for you, right? You can't see like above and below. So, if you were that red point there, you could move forward or backwards, but that's it, right? You couldn't move like that way, or come off the page. You couldn't do any of that. So because there's only one degree of freedom, forward and backward, that's the only degree of freedom that you have, this is a one-dimensional object. Okay? Any question about it? Finally, concerning this, now there's two different kinds of things that live on the real line. This is a point, or if you like, a location. Okay, so you could say like the green point could be talking to the red point and say like, hey, where do you live? And then the red point could say, there. So it's a location. Now, here's a different kind of thing. It lives on the line. Okay, so now what this is a little one-dimensional arrow. Now, its length is exactly that. It does not extend to the left. So this is where it ends. This is called the tail. This the head. And we could get out a ruler. That is to say, a linear measuring device, not an autocrat. And we could measure it and say, oh yeah, it's 1.5 centimeters or whatever. Okay, whatever ruler is appropriate for the thing in question. Okay, such an object is called a vector. All right. Now, here's another vector. Okay, so the green one. Notice that if you get out a ruler and you just measure its length, then the green one's bigger, right? It's longer. But nevertheless, there's some kind of qualitative difference between them. What's the qualitative difference between these two? The direction of them, okay, is different. So notably, what I want you to see is that the direction of the world in which the red and the green vectors reside is its sense is to the right. Do you observe that the red one is in agreement with the world, and that the green one is not in agreement with the world? Okay. As a result, these objects have something called assigned length. Okay. You can calculate the assigned length by taking a ruler, measuring. Okay, you measure it, and then it reads out maybe like 1.5 centimeters, and maybe this one's like 3 centimeters. Okay, but one of these is positive, and one of them is negative. Which one is positive and which is negative? The red one is positive. So this one is positive because it agrees. With the world arrow. Okay, the green one is negative. Interesting. Any question about this? So now vectors, and this is something that you have to get accustomed to, is that notably vectors do not have a position or a location. So, what I mean to tell you is that here's a vector. Okay, that's a vector. By the way, is this positive or negative? Positive. And then here's a vector. Okay. Are these the same vector? Yes. They're the same. They're the same, if I was a perfect artist, if I had a perfect hand. They're the same because they have the same length and they're pointing in the same direction. Doesn't matter where they're located. Now, these 2 points, are these 2 points the same point? No, they're not the same point. What if I draw another red one on top of this one? So now there's 2 red ones right there. Are those the same point? Yeah, because they're in the same location. Okay, any question about this? Good. So vectors are not located at any place in particular. Points are located at places. Does that answer it? Right. Yeah. So then I could draw another one. And then ask, are these 2 the same? And the answer is no, they're not the same. They're not the same because one of them is clearly they're clearly not the same length. Other questions? Good. So that's the situation on the real line. We've got vectors and we've got points. All right. Now, so some of you, when I said, when I brought up the issue of the arrow, a lot of you said, well, that's just the way we do it, something like that. And you're right, that is the way we do it. Everyone in the civilized world that does mathematics of any kind, every time they draw the line, in an abstract way, the increasing direction is always to the right. Okay? The reason in the end comes down to the fact that, something like 90% of all folks are born right-handed. So there's a strong right-handedness convention, so the increasing direction is to the right. Okay, so we're going to continue this right-handed bias for a little bit. So we could have R2, which means that now we've got, instead of there being a single number, now we've got 2 numbers. Okay. So the usual convention is like this. Okay. These two axes are at right angles to each other. And this one is just like a copy of the reals, okay? And this is another copy. But one of them is reckoned to be the first copy and the other the second. Which one is the first one? This one is the first one, and that's the second one. Okay? So this is the first axis. And this is the second axis. And yes, I agree that it is usually the case that we refer to them as X and Y, but there's nothing sacred about those letters, so I'm not going to use them right now. So to figure out a location, you know, to single out a point, say, we could be somewhere like right there. Okay, anywhere on this plane, in fact. Now, because on the plane you can travel horizontally and also vertically, that means that this plane has what dimensionality? 2, right? Good. So now, to specify where you are on the plane, that means that we're going to need, instead of just a single scalar, like on the line, we're going to need 2 scalars. So the way that you determine that scalar is you could come to here and say, okay, well, on the horizontal axis, now that we've dropped that down like that at a right angle, we can take a measurement on the horizontal axis. Suppose that it turns out to be A, measured on the horizontal axis. And then similarly, we could drop this over to the vertical axis and make a measurement there. And then we could get this to be B. And then that means that the name of this point in this coordinate system is what? AB. Notably, the order is significant. So it means A in the first direction and then B in the second direction. Any question about this? So that's a location. This is called a rectangular coordinate system in the end, because every location is at the corner of a rectangle. Okay, except for like, you know, there's some like trivial rectangles. Like if you happen to be on the horizontal axis, then it's a rectangle, but it's you know, flat. You know, it's squished, a one-dimensional rectangle. Good. Any question about this? Now, here's the deal, is that in R2, just like we have locations, like so, we also have vectors. Okay, so here's an example of a vector in R2. Okay, so that's a vector. So what that is that's a little oriented one-dimensional piece. So now what I mean by that is that if you were on the red and you were a little bitty creature and you had to stay on the red, do you observe that you always must either travel with the red or against it, but you can't travel any other way if the rule is that you have to stay on the red? As a result, this is a one-dimensional object. So this is a one-dimensional oriented thing sitting inside of a two-dimensional world. It has the same property as other vectors. So you could take, so for example, this one, say, those two vectors are the same. You know, if I were like had a perfect hand, they're the same because the location of the vector doesn't matter. Okay, so but you've got to understand what I mean is that you know, if I were to take this one, so these two are the same. Those are the same. But you know, if I take a copy of this and then I move it over here, but I also give it a twist and say, you know, maybe like this, then I could ask, well, are these the same? And the answer is no. Okay, now I agree entirely that I could, like, you know, pick this up and, you know, like do that. But to be equivalent, you're not permitted to rotate the vector at all, only rigidly, horizontally, or vertically translate it. Okay, so no twisting. Any question about this? Good. So now, the right-handed convention, just like the R1 has a right-handed convention, there's a right-handed convention for R2. The right-handed convention is the following: is that if you take, well, let's back up just a little bit. So this is a one-dimensional space, okay, and the creatures that live in there, like the most important creatures that live in there, are these one-dimensional denizens. Okay, these little one-dimensional things. Now, there's two-dimensional things that live in here, but we don't really talk about them a lot in this class. But I find that if I don't talk about it at least a little bit, students can get seriously confused about the issue. So, a line segment, okay, is a one-dimensional object. What's the corresponding two-dimensional object? Close. So I just want not an unbounded piece, but a bounded piece. So a rectangle, right? A rectangle. It's a two-dimensional thing. All right. So now, here's the rule: is that we've got a rectangle, and suppose that it's made by the two following kinds of vectors. So it's got a little horizontal bit like that, and then it's got a vertical bit like this. And then from here, now we'll complete the corresponding rectangle so that it looks like this. Okay, so that's a rectangle, but it's not the way that you usually draw a rectangle, because usually when you draw a rectangle, you don't put little arrows on it, right? But we've got to do that here, because what we want to do is we want to be able to say, is this going to be, you know, we can measure base and height and then ask, and then find out, oh, its size is like, you know, 12 or what have you. Maybe it's like 3 by 4. Then the question is should we assign it the value of positive or negative? Okay. Well, the way that you figure out assigning it positive or negative is we do have the following rule: is that you make a swirl by following the first axis first, and then the second axis. Okay, so what I mean is this. The first axis is the horizontal one. So we're going to swirl like this. So we'll follow the first axis, and then the second, and then come back around. So you can see it's swirling like so. All right. So here's an alternative rectangle that has the same size. And again, now notice that the distinction is that now the red arrow is on the top. So we've got to follow the red arrow first and then the green arrow. All right, so how will it swirl? Well, like this. Okay, now here's the thing. Can you see that this one, if you trace it, is going counterclockwise? And this one is going clockwise. Now, let's have a look at this plane. Let's make a little swirl. And remember, the rule is always follow the horizontal bit first and then the vertical bit. Okay, well, we can do that right here in this little corner. Follow the horizontal bit first and then the vertical bit. Okay, so this symbol, this swirl, okay, is analogous to this arrowhead. So that arrowhead is telling you how to measure the positive sense in the line. This swirl is telling you how to measure the positive sense in the plane. So these two rectangles, they both have the same base and the same height, which means that you know, if we were in 4th grade or whatever, we could get out a ruler and then we'd say, they have the same area. But you know, this is not 4th grade anymore. This is at least 5th or 6th grade, right? So one of these is going to be reckoned positive and the other negative. Which one's going to be reckoned positive? That one will be. Why that one?
Rotation matches the plane.
Because it's in agreement with the world. You see that the world is going counterclockwise. This one is going counterclockwise, so that means that this is the positive one. So this one is positive. And then, this one is negative. Now, to continue the right-handed domination of mathematics, do you observe that if you put your right hand on the page and stick your thumb out, notice that the positive one, that's the direction that your fingers go. Okay? So that's the right-handed convention, but in 2D. Okay? So the right-handed convention in 1D is, increase to the right. The right-handed convention in 2D is that the swirl has to agree with your right hand. Okay so far? So, now, we don't talk about it in this class. It's a shame, really, in my opinion. But these are little one-dimensional oriented bits. So those are called vectors. But just like there's little one-dimensional oriented things in the plane, you can also have two-dimensional oriented things in the plane, and those are important, and we talk about those, but not in this class. The place where you end up talking about it at least a little bit is that in physics you talk about something called like torque, okay? And then they tell you, that you've got the force and the distance it's applied over, and the torque is orthogonal to that. No, it's not. They're just lying to you. Okay, what torque really is actually one of these. It's a two-dimensional oriented thing, and your physics teachers are just straight up lying to you. Good. Any question about this? Let's continue. Now in R3, we want now, instead of there being a two-dimensional space in which the action occurs, now there's going to be a three-dimensional space. So we want to know how to draw it. So in the first place, this requires a little bit of skill, okay, and imagination for that matter, to draw it in a way that's sensible. So we need to draw three separate axes. All right. So the first one will be like this. So far so good. Or not the first one, but the first one I draw and the second one I draw. So both of these are in the plane of the page, meaning that if I turn the page, then these turn with them, right? Now I want to draw a third axis, but I'm going to draw it on this two-dimensional surface. Okay, so we have to use our convention about perspective. I'm going to draw another axis that's going to be coming out of the page, like the pencil that's coming out of the page. Okay, so like so. Okay, so this is coming out of the page. But the other two are in the plane of the page. So now, we're going to stick with the convention that, when you write a function like y is f of x, the input is x and the output is y. And then usually this is the x-axis and the y-axis. But if we have a function that has two inputs, x and y, and the output is z, okay, in the end, we want the output axis to be the vertical one. So this is going to be the output axis, and as a result, because there's three variables, that means this one's going to be the third axis. And then usually, we're going to name it z. Then, we've got these other two axes. One of them's the first and one of them's the second axis, and, x and y. The question is which one is which? Because if it, yeah? Because this is, I'm writing down the convention for you. Your question is like asking, why do we draw the arrow going to the right when we're drawing R, the reals? And the answer is, well, we have to agree on something. And I'm telling you that that you agree with me that this is the third axis. So that being the case, now we have to decide if that is decided, then which one is the first and which one is the second?
The one which goes to the right would be the first.
You would think.
You think?
You'd think, but the answer is no. This one is in fact going to be the second axis. And we're usually going to call it y, and then now by process of elimination, okay, this one is the first axis. And we're going to call it x. Now, that's a little bit disturbing because I know that historically speaking, it's been the case that the horizontal axis has been x for you forever. Well, it's just not going to happen anymore. All right? So, now here's the deal, is we want to figure out, now why should it be this way? Why should it be this way and not the other way? All right. So now this, if I draw this going back, that's now behind the page, right? That's behind the page, and this is continuing going this way a little bit. If we take the orientation of the plane from the previous page, remember that we're going to follow the first axis first and then the second axis. So in the plane of this page is a little swirl. It looks like this, right? Counterclockwise in the XY plane. You know, so what I mean is like it's just like I took this and then made it be like that. You know, like that. Can you see it? So now, this is what the orientation in the XY plane, and then to continue, this is the positive direction for z is going up. The positive direction for z is going up. So now here's the thing. If you put your thumb going in the right thumb in the z direction, okay, in the z direction, do you notice that your hand will curl from your fingers will curl from x to y if your thumb is pointing in the z direction? But if you swapped them, then it wouldn't work. As a result, the way that you signify the orientation in three-dimensional space is like this. This with a swirl. So that's going behind. Notice that that's in agreement with your right hand. So that's the positive convention. So this is positive. And then the negative one is this. And then like so. And in case you didn't catch it, I'd like for you to observe that this is the three-dimensional orientation, okay, the right-handed orientation. Now, if we look at all the orientations that we talked about, the 1, 2, and 3, then notice that they all look like this. This is the positive orientation for a one-dimensional element, a right arrow. And for negative orientation, it's this, a left arrow. For a two-dimensional positive orientation, like so. And for a one-dimensional positive orientation, like so. Okay, and then for a three-dimensional positive orientation, like so. For negative orientation, like so. And now what I want you to observe, in case you didn't notice it already, is that if I was to put a mirror right here, can you see that that's what the other one would see across the mirror? In your mind's eye, imagine standing in front of the bathroom mirror and holding up your right hand. What hand is the person in the mirror holding up? Their left hand, right? If you were to just go up there and high-five them, like high-five the person in the mirror, they're holding up their left hand. The orientations can be visually obtained by imagining what it would be like to look across a mirror at it. And there's a lovely reason, I said it pretty forcefully. Your physics teacher's just straight up lying to you about torque. They are. And the reason is because imagine looking at the same situation, someone pushing a torque bar across a distance, but imagine looking at them in the mirror. Which way would the torque be going then? And your physics teacher can't answer that question, or they'll say, oh, I don't want to talk about it. Okay, any question about this? So this is the right-handed convention. So what I want to be clear about is that, let's say like this. A typical calculus problem, differential calculus question, is something like, well, what if someone jumps out of an airplane, and they've got a parachute or what have you, hopefully, and if their elevation, we denote their elevation as y, and time is t. So they jumped out of an airplane. Then we could calculate the derivative dy dt. What should be the sign of the derivative? If someone's elevation is y, a function of t, and they just jumped out of an airplane, what should be the sign of dy dt? Should be negative. Why should dy dt be negative? Yeah, because they're falling, right? So your dy dt represents how is their elevation changing in time? Well, they're going down, right? So dy dt should be negative. So on such questions, one of the things that the graders do in differential calculus is that the instructors give you a question that's more or less like, someone jumps out of an airplane. Now calculate something about their derivative. If you respond by saying something like, therefore dy dt is 10, then if it's my course, then I just tell the grader to just give you a 0, because that's nonsense. That's what that is. What you're telling me is that as a result of jumping out of the airplane, you have begun falling up. Okay? It's nonsense, right? That's not the way it works. So dy dt's got to be negative. The reason why I'm telling you this is that you're going to have to draw various, not too much because this is not an art class, but you're going to have to draw and understand pictures. And if you draw a three-dimensional picture but you don't have the right-handed convention, if you draw the left-handed one, then that's nonsense. In the same kind of way that you don't fall up, you fall down. This rears its head in science a lot because molecules have mirror reflections too. So like, the smell of lemon, can you imagine it? Oh yeah, it smells good. Okay, so then if you take a lemon molecule, okay, and then you reflect it across a mirror, then there's another molecule, right? It's another molecule, but it's not the smell of lemon. Do you know what it is? It's the smell of pine. Amazing. And there's lots of little bits like that. That if you're in chemistry, you're going to end up having to deal with that. Any question about this? Good. Now let's get to some actual calculation. Okay. So let's draw the plane. Say y is equal to 5. This is a plane. Okay. So in the first place, let's draw ourselves a three-dimensional space. So now this is using the convention that all points are x, y, z. Okay, so now which one is which? Uh-huh. Uh-huh. Very good. Okay, so now you can imagine it like this. We could say that in this room, say, the x-axis is like this seam running in the front here. Okay, that's the x-axis. And the y-axis is the seam over there. Okay, it's got to be that way, so that up, so that it's right-handed. It's got to be that way. Okay, so now we're saying y is 5. Now, if you look at the floor, it's got little tiles on it, and we could say like maybe that's like one unit. Okay, so then just from the wall there, I can just count 5 times. So let's say that I'm standing on 5 tiles from the wall. Okay, so my feet are on a point where y is 5. Are there any other points whatsoever where y is 5? Where?
Point this one, and
Yeah.
as you walk forward.
Yeah. So like I'm walking on points where y is 5. So is it like all of these? Are there any others besides those ones?
All the way out as well.
Yeah, like my hand here. Also is it y is 5, right? Because the question in the end is it's everywhere. It's 5 from the wall. So it's plane, and it's all of this stuff here. Just like the ceiling, is it's also a plane, more or less, and it's at some fixed height. Okay, so the way that you draw the plane y is 5, it's you're saying I want the collection of all points where y is 5. Okay, well it doesn't matter about x and z because this doesn't depend on any of that. So let's just mark out this. So like 1, 2, 3, 4, 5. So that point right there is y is 5. Okay, but this whole thing right here. So now I'm going to draw a line from here, but I'm going to draw it parallel to this. And the way that my trick, okay, that can be your trick too, is that when you want to draw a line parallel to another one, make the first line point directly at you. And then draw this one directly at you. Like that. So this is like all the points that were on my feet, And then now from here, I want to go up. And so now, I'll draw another one going up. And another one like this. Now you have to kind of use your imagination a little bit. That's a piece of plane. It's a plane. I can't draw the whole thing, right? Then you couldn't make sense of it. But you could imagine that's like a little wall partition, like a cubicle thingy. I just drew part of it. Okay, so this is the plane, y is 5. Any question about it? So z equal to a constant would be just like this, but it would be a ceiling instead of a wall. X equal to a constant would be just like this one, but instead of being parallel to that wall, it'd be parallel to this wall, like the screen there. Any question about this? Good? This is okay? All right. So now we're going to bring up distance. And we're just going to have time to bring it up, not time to fully flesh it out because we're coming up against the clock. But again, we're going to do it in this kind of way. In R1 first. So now, in case it wasn't clear, the reason why I'm always going to draw the reals with just a one arrowhead is because if I drew the other arrowhead going the other way, that would be ambiguous. Like, okay, what are you talking about? You can't be increasing in both directions. So what if we have this point here and this point here? And these are points, which means that they're specific locations. They're not vectors. So there's suppose we measure the location of that and it's A, and we measure the location of that one and it's B. And then the question is what is the distance from A to B? Now, when I say distance, I mean the unsigned distance, not signed distance. Okay? Just like, if you were to say the distance from Dallas to Houston is 200 miles, you wouldn't say the distance from Houston to Dallas is negative 200. Right? Not like that. I'm talking about unsigned distance. And the question is that what's the formula for this? Okay. So then the distance is, well, for this specific picture, it would be b minus a. But if I was to make a different picture where the red and the green were in the other order, then it wouldn't be b minus a anymore, it'd be a minus b. But y'all told me, I heard you say it. How do we make sure that we always pick out the positive one? Absolute value. But in fact, I'm going to write it like this, for reasons that aren't entirely clear yet. I'm going to write it like this. The square root of b minus a squared. That's the distance between those 2 points. Okay, now, here's the deal. Okay, and this is something I want you to think about before next lecture, is I want you to consider, is this true? Is this true? The following is the following. True. For all x. Okay, so don't answer. I just want you to think. Is it true? The square root of x squared equal x. So it's a question. And then on Wednesday, when we come back, I'll ask. Okay? So welcome to the university, to those of you who are new, and I hope you all have a wonderful Monday.